y'all. How are you doing? Back for another science hour. Darrell Berber Jr. We're going to continue with relativity part 2. I did finish solving um, that problem with area. So I'll see if the mathematician is here. I was planning on starting that early. So if he's here now, I'll probably start that in a moment. Otherwise, I'll probably end with that. And we'll spend some time going through uh, updates on relativity. I'm just checking to make sure everything is streaming fine. Everything looks fine on my end. So be sure to let me know if there's any issue with audio or anything. And I'll give a brief review of what we covered last time. It's like everything okay. So we talked about some of the basics of relativity. I'll pull up my share screen. It's my Patreon, by the way. Anybody would like to join? And here's the, oh, hold up. This textbook was actually in the elsewhere. There we go. So we were in this textbook. We had started with the first two sections. We're moving on to time dilation today. And one of the things I noticed is that the Michelson-Morley paper is mentioned 3 times so far. So we'll delve into that paper a bit. Perhaps over the next few weeks, we'll read the entire paper. So for instance, looking at this section right here in this textbook, it says light travels at the same speed in each frame, but it takes more time to travel the greater distance in the earthbound frame, which we'll get to. But this is referring to the Michelson-Morley experiment. At least it was the first time that we were able to determine that light travels in the same, takes the same speed no matter the frame of reference that's perceiving it. And I saw that in a lot of textbook as well, which I'll bring up a bit later. So it looks like the mathematician isn't here, so we'll go ahead and start with the relativity, and I'll end on the area problem that we had a few weeks ago. So this is the time dilation section, and recall that we spoke last time about how physical laws are invariant, meaning, for instance, Newton's laws work the same whether you're moving or stationary relatively, as long as you're moving in a inertial reference frame, meaning that you're moving either at a constant velocity or you're stationary, you're not moving at all. So basically, any two different frames of reference where one is moving and one is relatively stationary, if they perform the same experiment, they should get the same result. Because as long as you're moving at a constant velocity, everything is the same. And if you think about it, it would need to be that way because the Earth is moving around the sun, is spinning, it's moving through the galaxy and so forth. So if all of these things were dependent upon velocity, then velocity has to be changing to some extent all the time. Even if you take just the motion of the Earth is moving at a constant acceleration basically as it goes around the sun. So basically, depending on what galactic process moves in what direction at what moment, our different experiments may behave differently. But since everything is at a large, even the acceleration of the Earth is at a relatively low pace as far as acceleration, but velocity-wise, it is a big difference. So being that the velocity doesn't make a difference because light travels at the same rate everywhere, it makes it work out. So we also talk in this chapter about measuring things, how basically simultaneity is dependent upon the perspective of the observer. So we saw this example here with the train where a light flashed. The observer on the train that was moving with the light caught up with the light on the right first and observed the light on the right flashing before the light on the left, as we can see in the second image here. But the person observing on the ground, because the emission of the light happened at an equal distance from the person's not moving, they saw it happen at the same time. So you can see how, depending on the movement of the observer, it does still change the simultaneity of things. So even though if the person on the train did a Newtonian experiment, they will get the same results as the person on the ground doing the experiment. When it comes to measuring timing of things, it could be a bit different depending on who's doing the measuring. So we'll continue with that and talk about time dilation. So this is chapter 5.3, and again, this book is the uh, free textbook that you can get online from OpenStax. Version 2 and some of version 3 of this book was utilized. Volume 2 and volume 3 was utilized in the one of the electromagnetism classes I was a learning assistant for. So these books are actually utilized in very good colleges. So there's some good information. And be sure to drop a line. Let me know if you have any questions. Holler if you're here, and I will keep everything going. So going on to the next section, time dilation. Explain how time intervals can be measured differently in the different reference frame. Describe how to distinguish a proper time interval from a dilated time interval. Describe the significance of the muon experiment. Explain why the twin paradox is not a contradiction, and calculate time dilation given the speed of an object in a given frame. So it says the analysis of simultaneity shows that Einstein's postulates imply an important effect. Time intervals have different values when measured in different inertial frames. Suppose, for example, an astronaut measures the time it takes for a pulse of light to travel a distance perpendicular to the direction of his ship's motion relative to an earthbound observer. It bounces off a mirror and returns back. How does the elapsed time for the astronaut measured in the spacecraft compares with the elapsed time that an earthbound observer measures by observing what's happening in the craft? And to highlight in the next paragraph, the time measured by the astronaut within a spaceship where the astronaut is at rest is smaller than the time measured by the earthbound observer to whom the astronaut is moving. And later, the book will describe these two time frames of reference as proper time and dilated time. So basically, the measurement of time that happens in the same location, the proper time, is going to be the shortest amount of time. You can almost say you could say perhaps maybe it's not quite accurate to say, but it could be looked at as the most objective time. It's the time that's measured at the same event, at the location of the event. Whereas the time measured from the person observing the moving event, that'll be the time dilated time, because uh, the distance that the event travels across will take more time to traverse that longer distance. Therefore, that time is dilated, is longer. So that'll be the difference. Light travels at the same speed in each frame, so it takes more time to travel the greater distance in the earthbound frame. So again, this is another time seeing this. So looking at my textbook that we're using now, for back in, this is the textbook we're using for my relativity class, my first course in general relativity. And I highlighted that it brings this up as well. The postulate of the universality of the speed of light was Einstein's great and radical contribution to relativity. It smashes the Galilean law of addition of velocities because it says that if v has magnitude c, and so does v prime. And v prime would simply be the speed of light as measured by an object that's moving. So basically, if you're moving with the direction of light, then technically we should measure a slower speed of light. And if you're moving opposite the speed of light, you should measure a faster speed of light, since those speeds combine, and you're calling that v prime, regardless of big V, which is the speed of light. The earliest detection, the earliest direct evidence for this postulate was the Mixon-Morley experiment. So we can see how this is brought up several times. It's brought up, uh, I remember right earlier in the University Physics Volume 3 book, I believe it was brought up in name in one of the previous paragraphs, but definitely is brought up now as far as um, the simultaneity of light. I think I scrolled pages by mistake. Light traveling at the same speed. So I figured we would take a look at that, and we'll get to a certain part in the paper. We won't get through the whole paper today, but perhaps each week we'll look at it a little bit because it's quite relevant. So this will be the Michelson-Morley paper. It was actually from the early 1900s, so this stuff has been going on for a while, in the American Journal of Science, 1887. So this experiment, we've known that about the simultaneity of light for a few centuries now. So the title of the paper, On the Relative Motion of the Earth and the Luminiferous Ether. So the idea is that the understanding was that the uh, uh, light moves in a certain wave fashion, which the paper will call the undulatory theory. Other people focused on the emission theory, like shooting a bunch of particles. Ironically, we hold both of them now. We have the wave phenomena that causes like the quantum effects, like the double slit experiment, and then we have the photon particle like idea with like the discrete energy package that, for instance, how radiation can boost the energies of an atom. So ironically, light is, I guess, neither, but it can be looked at either way. But this is one of the papers I found I was talking about, because I was like, what do they mean, the undulatory theory of light? So we look at this paper, it basically mentions it. This is by Paul Epstein, Centennial of the Undulatory Theory of Light. The emission hypothesis contended that a luminous body projects into space tiny particles which enter and affect our eyes. The undulatory hypothesis regards light as a wave-like motion of a hypothetical medium, which was supposed to fill all space and to penetrate all transparent bodies. This medium was named the light ether. So this is what Michelson and Morley called the luminiferous ether, this light ether, which the idea is just like how sound moves through the medium of air. Basically, light moves through a medium of ether. The discovery of the aberration of light was soon followed by an explanation according to the emission theory, which again is like photons, packets of energy, like we just read. The effect was attributed to a simple composition of the velocity of light with the velocity of the Earth in its orbit. So the theory was that there's these particles floating around with a finite velocity, and the movement of the Earth relative to these movement of these particles will either add to the velocity or subtract from the velocity, like we were talking about with the train. The difficulties in this apparently sufficient explanation were overlooked until after an explanation of the undulatory theory of light was proposed, which, as we read, is the wave-like theory, the idea that light is a wave. This new explanation was at first almost as simple as the former explanation, but it failed to account for the fact proved by experiment that the aberration was unchanged when observations were made with a telescope filled with water. For the tangent of the angle of aberration is the ratio of the velocity of the Earth to the velocity of light. If that's the case, since the latter velocity in water is 3/4 its velocity in a vacuum, the aberration observed with the water telescope should be 4/3 its true value. So let's look at the math that they're talking about here. Okay, hold on. looking at something earlier. Give me a moment. Let me go to the proper notebook. So we'll take a look and see what they're talking about here. So they said that the difficulty in the analysis they were talking about is because in water, the aberration that we observe in light should be 4/3 its true value, right? So let's talk about what the aberration is, and we'll do a calculation on that briefly. Right. The idea is that the aberration of light is basically the idea that just like how when we're, for instance, riding a bike or ride my bicycle a lot, if you're riding in the rain and you're moving, even if the rain is coming straight down, if you're riding on your bike, it seems to be coming at an angle. So the idea is that uh, when we look at light through telescopes, we can see that there's an aberration that it comes in at an angle, just like how light comes in at, just like our rain comes in at an angle when we're, moving. So the idea is basically in a vacuum, we have the speed of light, c. Let's say light is coming down this way from the sky, and we have the Earth moving. Let's say the Earth is moving that way. So we call this C, and we call this V. What'll happen is, because we've moved, we would sort of see the light taking a sort of um, altered path, like so. So this angle here would be the aberration angle. And the paper said that the tangent of the angle of aberration is the ratio of the velocity of Earth to the velocity of light. It's simply talking about how tan equals opposite over adjacent. And if we look at this angle theta, so basically tan of alpha, so tan of alpha equals opposite that angle is V over C, right? So tangent of this angle that's being made from the aberration of light. So this blue line is the aberration of light here. Due to the movement of Earth that way and light coming straight down, we perceive it at a slight angle, alpha, and this is what they mean by the tangent of that. Where the 4/3 would come in from, if we have water as our medium, when light comes down, it'll be a little bit, the vector will be a little bit shorter because it'll be 3/4 what it is in a vacuum. See if I can get this thing to make an arrow again. There we go. It'll be a little bit shorter. It'll be 3/4 C, and Earth is still moving in the same direction. The Earth is moving like so. And the aberration of light will be slightly different. The angle will be slightly different due to the difference in vectors. And that'll show up in the tangent. So basically, now tangent, we'll see of alpha 1, to use the notation that the Michelson paper will use in a bit, is going to be the new opposite over adjacent 1. So that's going to be, this is still V over 3/4 C. Right? Since the 3/4 is in the denominator, it becomes 4/3 V over C. So that means that here, alpha equals the inverse tan of V over C. And on this one, alpha 1 equals the inverse tan of 4/3 V over C. Right? So that's where that's coming from. When we would go back to the paper, you can see what it means by that. Or if the tangent of the angle of aberration is the ratio of velocity of the Earth to the velocity of light. And since the latter velocity in water is 3/4 its velocity in the vacuum, the aberration observed with the water telescope should be 4/3 of its true value. And what they're noticing is that they were not seeing that. Uh, on the undulatory theory, according to Fresnel, first, the ether is supposed to be at rest except in the interior of transparent media, in which, secondly, it is supposed to move at a velocity less than the velocity of the medium in the ratio. And I can't tell what that exponent is. It's 2 or 3. It seems like where n is the index of refraction, like with Snell's law. These two hypotheses give a complete and satisfactory explanation of aberration. The second hypothesis, notwithstanding its seeming improbability, must be considered as fully proved first by the celebrated experiment of Fizeau, and secondly by the ample confirmation of our own work. And there's some secondary information here. And we should probably read this one and maybe notice that most writers admit the sufficiency of the explanation according to the emission theory of light, while in fact the difficulty is even greater than according to the undulatory theory. For on the emission theory, the velocity of light must be greater in the water telescope, and therefore the angle of aberration should be less. Hence, in order to reduce it to its true value, we must make the absurd hypothesis that the motion of the water in the telescope carries the ray of light in the opposite direction. Now, I'm not actually clear why the velocity of light would be greater in the water telescope. Um, so I'm not sure what they mean by that one right there, but seems like an interesting aside that they took the time to put it there. If the Earth were a transparent body, it might perhaps be conceded, in view of the experiments just cited, that the intermolecular ether was at rest in space, notwithstanding the motion of the Earth in its orbit. But we have no right to extend the conclusion from these experiments to opaque bodies. But there can hardly be question that the ether can and does pass through metals. Lorenz cites the illustration of a metallic barometer tube. When the tube is inclined, the ether in the space above the mercury is forced out, for it is incompressible. And he says it may be objected that it may escape by the space between the mercury and the walls, but this can be prevented by amalgamating the walls. So probably this is some experiment or some idea about ether real and what it would look like in tubes. But again, we have no right to assume that it makes its escape with perfect freedom. If there be any resistance, however slight, we certainly could not assume an opaque body such as the whole Earth to offer free passage through its entire mass. The idea that the ether should be slowed down by the Earth, it seems like. But as Lorenz aptly remarks, and I thought they were going to translate this, but apparently, see if they translated it somewhere. Looks like they didn't. But from what I can tell from the French, it's saying what in the question, an important question is the consideration on the degree of probability or of the simplicity of one of the other hypotheses, but to address the experience and to know and to understand about movement of the surface of the Earth. So it's talking about the different probabilities and some experience. In April 1881, a method was proposed and carried out for testing the question experimentally and deducing the formula for the quantity to be measured. The effect of the motion of the Earth through the ether on the path of the ray at right angles to this motion was overlooked. So it's quite interesting. And he said it may be mentioned here that the error was pointed out to the author of the former paper by Aimé Portier of Paris. So apparently, either Michelson or Morley did an earlier experiment or somebody else did, but it didn't take into account the movement of the Earth relative to the light at right angles, which we'll see in the illustration that follows in a bit, and we'll work through that illustration. The discussion of this oversight and of the entire experiment forms the subject of a very searching analysis by A.J. Lorentz, who finds that this effect can by no means be disregarded. In consequence, the quantity to be measured had in fact but one half the value supposed, and as it was already barely beyond the limits of errors of experiment, the conclusion drawn from the result of the experiment might well be questioned. Since, however, the main portion of the theory remains unquestioned, it was decided to repeat the experiment with such modifications as would ensure a theoretical result much too large to be masked by experimental errors. So basically, they're counting the lack of accounting for that lateral motion as experimental error. They're improving the experiment to basically eliminate that. The theory of method may be briefly stated as follows, and we'll go through the image so we can see the image here. What I'll do is switch to an image I have from the paper, and I'll highlight what he's talking about. This is going back to the pad. Enlarge this a bit, and we'll see what we have. So it says, let SA, figure 1, be a ray of light which is partly reflected at AB. So basically we have a light coming down here, is partly reflected in AB. So part of it comes down and part of it goes back, and is partly transmitted in AC. So part of it goes here. So then we have that same beam of light broken into those two directions, being returned by the mirrors at BC along BA and CA. So this is a mirror. This is a mirror. And basically it's bouncing the light back like so. Right? So I think I highlighted the wrong S. This is actually S here. So the light is coming in through here through SA, partially being split to come up this way and come down, partially being split to go that way and come back this way. BA, which would be this one coming back down, they're going in the order from B to A, and the way they list it is partly transmitted along AD. So part of that is coming this way. And CA is partly reflected along AD. So CA, which is coming from this side, is partly reflected here. The pads AB and AC, which is these major pads here, equal, the two rays interfere along AD. So the idea is that the length of everything is set up so that by the time the rays get back, perhaps the rays were like this when they first left, aligned with each other. Perhaps when they get back, they look more like this, where they may interfere and cancel each other out. Or, yeah, I mean, I don't know how the constructive interference will work. I suppose it can still constructively interfere and boost itself, but I wonder if it could actually boost itself. Think about that. But interference strikes me mostly as destructive interference. AD, suppose now the ether being at rest, that the whole apparatus moves in direction SC. Right? So now we have the entire thing, and the thing is sitting on the earth, so we can imagine that the earth is moving this way. And I'll call this V. the direction and distance traversed by the rays will be altered thus. The ray SA is reflected along AB, the angle BAB being equal to the aberration alpha. So basically this angle here, alpha, will be equivalent to this angle that we have here, the angle that's uh, uh, brought about from aberration. Now, one interesting thing is uh, this angle here is basically half the angle if you think about it. So technically, it seems like when they say uh, BAB, oh, no problem, mathematician. Welcome. And I'll do your problem at the end. I was going to start with it, but I noticed he wasn't here, so and it's no biggie. I'll finish the relativity thing, and I'll just do it at the end. Pickleball. I'm not sure what that is. Let me take a look and see. It looks something like tennis, huh? Tennis with a much smaller racket. Oh, seems strenuous. So it depends on how fast you hit. I know tennis can be very strenuous, but I don't think I've ever seen a pickleball. Do you play at school or do you play like amongst friends in your neighborhood? Like who do you play with? Like are you on a team? Oh, I'll finish at the top of the hour, around the top of the hour, probably a little bit before that. Normally, I like to keep these shows around an hour. Sounds cool. Good to have something you like to do. Yes, I figure about around 15 minutes. So these usually I try to keep about an hour, all together about an hour. So where was that? Yeah. So the light is bouncing back. Oh, now it seems like this angle. Oh, okay, sounds good. By the way, I'll probably be ended in 40 minutes. So you probably want to come back in like 20 minutes. Now the thing about this is this angle, it might be because they're using the small angle approximation, because sine of theta equals theta when the angle is very small, just like tan of theta equals theta when the angle is very small. Sounds good. I'll see you then. So I wonder if they're using that approximation to sort of call both sides of this thing theta, because I guess the approximation it won't really matter much. You can see that approximation when you're getting like distances to planets and stuff like that. Distances to stars with parallax. The angle BAB being equal to the aberration AS, right? Is returned along BA. So basically, remember that the planet is moving this way, so the whole apparatus moves a bit that way. Now, the thing is, technically, from the perspective of the apparatus, the light is just going up and down. But from an observer looking from the side, the light is sort of going at an angle, and it bounces in that way. And ABA equals 2A. So it's saying that ABA prime, this distance, going both of these ways is the same as 2A. So it seems like they're definitely making an approximation because this distance would be a slightly longer than A since it's at an angle. And this one would be slightly longer than A since it's at an angle. But it looks like they're, doing an approximation there. When it goes to the focus of the telescope, so they basically have a telescope here capturing it. This is where we will capture the aberration, whose direction is unaltered. The transmitter ray goes along AC, it's returned along CA, and is reflected at A prime, making CAE equal to 90 minus A. So we're looking at this angle here. This angle between here is still alpha, and they're bouncing the light off of this angle here. So that 90 minus alpha is this angle. So basically this is alpha, This is 90 minus alpha, so this whole thing is 90 degrees. So they set it up to be that way, and therefore still coinciding with the first ray. And of course, understanding the speed of the motion of the Earth is relatively easier to calculate what that angle should be. It may be remarked that the rays B prime, BA prime, and CA prime do not meet exactly at the same point A prime. It may be remarked that the rays BA prime and CA prime do not now meet exactly in the same point A prime. Those are differences of the second order. This does not affect the validity of the reasoning, but it now be required to find the difference in the two paths ABA prime and ACA prime. So the idea is that does this distance here match this distance? Do those distances match? And some calculations are going to come after that. Now, I had mentioned last week about the light well, the light clock, I meant to say. So this actually goes directly back to what we were discussing in the textbook with the light clock. So this is the astronaut that we're talking about. And if you look at this thing here, this is basically an illustration or a depiction of the light clock, even though, as far as I know, they don't mention it in that perspective at this point. So the idea is that the astronaut here, this is what would be proper time, because the astronaut, the mirror, the astronaut is seeing the entire experiment occur in the same location, even though the light is moving, the light beam is moving up and down. The mirror is in the same spot, the receiver is in the same spot, the light source is in the same spot, the astronaut is there with them. So even though the entire satellite is moving or spaceship is moving, inside the spaceship, everything is moving together. So in that frame of reference, we can basically call that frame of reference how I normally would note it. This would be S prime, because the entire frame is moving at speed v, and the observer on Earth, which would be this person here who's watching the spaceship go by, and let's say looking through the window of the spaceship to see the experiment, this will be the frame S, which is stationary, watching the prime frame move. So this frame here will be proper time, because this is the frame that's moving and this is the frame that contains the experiment, and the astronaut is here floating around and so forth. So this will give us proper time, which is the shortest amount of time that you can measure in an experiment, the shortest time possible. The shortest time possible to be measured between two events will be measured by the observer in proper time that's moving with the event. And this observer will experience time dilation, meaning time will take longer, and we'll actually do some math to show that's why that's the case, and then we'll go ahead and end there and continue next week on the relativity. So let's go back to the pad. So basically, again, this is like a light clock that'll allow us to get distance and time. So on the left side, we have the mirror, and the light beam here is going up, coming back down to the receiver. All of this is happening in the same spot. And the distance D is the distance between the mirror and the light source and receiver, right? L here is 0. Like there's no distance between the light going out and coming back, or it's quite minuscule. And again, this side will be proper time, is moving with the experiment. Now, deleted time, we'll see something quite different. So basically, the light will be going like so, and then coming down like so, because looking at the experiment from the side, the entire ship is moving. So in your vision, it looks like the light goes up like that and comes back down that way. In our perspective, in our vision, similar to how if someone is walking and they throw something up in the air, if they're walking, they catch it straight in their hand because the object is moving as well. When you look at it from the side, it looks like the object makes a sort of arc in the sky. So this is the same thing that's going on. Now, the thing about this arc is this arc has the entire experiment in each part, right? So basically, this is the instance when the light is emitted. This is the instance when the light hits the mirror. And this is the instance when the light hits the receiver. And this is what the person on the ground is basically seeing this entire thing move along to the side and be captured, right? So what we can do is we can go ahead and model the scenario on this side, the dilated scenario, by drawing a nice triangle. And then we got to apply some basic algebraic and trigonometric uh, scenarios, like for instance, uh, velocity equals distance over time. And it's customary or convenient to divide these up into two different distances, L and L. So we can say that the distance here is 2L, and it goes a certain over a certain amount of time, it covers that distance. And the velocity here is c. So we could say v equals 2L over change in t, which means we can say 2L equals v change in t. We can say L equals v change in t over 2. So this is basically outputting the length of one of these lines in a triangle in terms of the velocity of the light that's moving and the change in time that it took to traverse this distance here. And again, this distance L here is 0 in the original frame, so it doesn't have to travel that at all. But this distance exists in this frame, thus light in this frame has to travel longer, so it takes longer period of time. And this is our irony of relativity. So I'll finish dividing this into 2. This is the same distance, d, from the mirror here. And again, the mirror, this is just like a 3 snapshots of the mirror in 3 different locations, the same mirror. As the spacecraft moves along, and we have that. And another thing that we'll utilize to capture this is identifying this length, because again, the light is going along this entire path from the perspective of the Earth. From the perspective of the astronaut, the light simply travels 2D, right? It travels there, it travels back, the whole path is 2D. From the perspective of Earth, the light travels S and S, and S is going to be the square root of d squared plus L squared. And now we have 2 of our components that will be utilized in the light to derive like things like the Galilean transformations and stuff, as I recall. This is how we end up getting or close to those formulas by seeing how things behave in these manners. Now let's see if there's anything else I can point out before we move to the map problem and close up at the top of the hour. Right? So those definitions, by the way, time dilation is the lengthening of the time interval between 2 events for an observer in an inertial frame. Now, this is an inertial frame because the spacecraft is moving at a constant pace that is moving with respect to the frame of the events in which the events occur at the same location. So in this case, they're speaking of the Earth as the one that's moving, as if the Earth is moving this way. at speed v, and this is stationary, and it ends up being the same thing. The event is still moving with the S prime frame. Therefore, the proper time is with the S prime frame because it's looking at the event move, and the event is stationary with respect to the S prime frame. So that's for an observer. Right? And proper time, we see that here, proper time interval change in tau between the two events is a time interval measured by an observer for whom both events occur at the same location. Because again, the person who's on the craft, they're just standing there, the experiment is there and it doesn't move. Only the person looking from the Earth sees the experiment move. Right? So we have that. That's pretty much that. We'll go ahead and close up soon after we do the math uh, 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 problem. And keep in mind that this will be the foundation of some of the things we'll talk about next week. As you can see, we'll get into the gamma, uh, uh, which I had forgotten about. I remember we had to do this in modern physics. Basically, it's like the um, parameter that allows you to change between different frames of reference given the speed of light. And this is our equation here. S squared equals b squared plus L squared. That's what we got from the light uh, 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 clock. So we'll continue with this math here now that we have these concepts down and go from there next time. Right? So let's go to the pad and we'll take a look at the map problem I was given last week. And I'll go ahead and start it on a new page. The idea is that we want to find the area of this here. So just say, what is the area of the central region? Ah, awesome, mathematician. And keep in mind, by the way, if you want to ever show some support, I do have a Patreon. I'll go ahead and show what it looks like really fast. You could even sign up to get a, just for a small amount for ongoing support, or you can sign up to get a detailed, full show devoted to just your problem that you want me to solve. So keep that in mind as well. Oh yeah, sure. I just started mentioning it, and we'll go briefly through it. So we wanted to basically get the area of this region. So the answer I'll just start off by giving the answer that I got for the problem. The answer I got is about 126 units altogether, or about 11.23 units squared. And so this is basically the answer I got for the area of that place. 126 units is just counting up all the units in an area, and taking the square root of that is basically the amount you would have to square 11.23 to get that area there. So the process, I'll run through briefly what I did was, you see that this area is pretty symmetric. Ah, sounds good. By the way, who's the author of that book, by the way? I went to look the book up, but I couldn't find it. Perhaps if I had the author, I'll be able to find that book. Maybe I could see some of the other problems in there. But basically what I did was, as I reminded myself about integrals and things like that, remember that we can basically take a part of this thing and integrate over that part and multiply by 4. So what I did was, and perhaps it might be harder to see it with the thick outline. We have here and here. So basically all we have to do is get the area of that section and multiply it by 4. Because as we discussed last time, it's clear that since this side is 20, this is clearly the radius of a circle. It seems to be an arc length of a circle. So that means that we have a radius of a circle that's 20. And if you look at this, we can actually use trigonometry to get the distances to these points right here. Basically, this is a point at the end of that radius. If I was to call this A, and this is a point directly in the center. Now, the way symmetry works is this part here is at 10, this part here is at 10, and this is also going to be 8. So basically, we can simply utilize trigonometry to figure out these angles. So for instance, this angle here, I'll call it alpha. You could utilize, for instance, we have that this outside height is 10. So we know that this is 10. We know that this is 20. So we can say that tan of alpha equals 10 over 20. So that means that alpha equals tan inverse. Oh, yep, there you go. So that's what I have right there. I rounded a bit. So the alpha is tan inverse of 0.5. And there we go. So we can get that alpha. And now that we have alpha, oh, you caught everything. You know, when you came, this is running. The whole detail thing takes a long time. It'll take like an hour. So so I'm giving you the outline of what I did to solve it, and you know, you'll be able to understand the processes and the steps to go. But it is a detailed process to go through everything, and is a pretty long integral. So, but suffice it to say that we, I can see from the symmetry that this is 10, this is 10. I already know that the radius is 20. So I can go ahead and get angle alpha. Then I can use angle alpha to get A, to get this length right here. And once I get that, what it's going to do is going to give me how thick this arc of a circle is. But basically what I want to do is I want to get the area of this, and then I can multiply by 4. And what I have here is the top of the arc of a circle. And what I have here is a line at the bottom. So maybe I should make the line a different color. So I have there an arc of a circle of radius 20. And I have here a line. And what I did, like I said last week, I used that to take integrals. But in order to get the upper integral, the arc length, I needed to know these two angles. And when I found angle alpha, I found out that this was 30 degrees. And then I utilized alpha to get this length A. Then I could utilize length A to get this angle here. I'll call this angle beta, and beta was 60 degrees. So now I have these two angles here. I have the angle on this side. I have the angle on that side. I know the radius of the arc is 20, and that allows me to get an integral of the upper end of this triangle. And so basically I parameterize this line, so we know that y x squared plus y squared equals r squared. So y squared equals r squared minus x squared. So y equals the square root of r squared minus s squared. So this is the equation of this line here. But now I know I need to integrate from these two angles, the angle alpha and the angle beta. So basically integrating from alpha to beta of square root of r squared minus s squared will give me the area of everything here. It gives me that entire area. And then I know that uh, I'll call this full area. And then I know that this is 10 high. That's just a line. So I know there y equals 10. And this is going to be from 10 to a right here, the length of that. This is going to give me the area of just this. And I have the integral of 10 to alpha, or 10 to a at least, the actual a of 10 dx. That'll give me the bottom area. I know, yes, yes. I'm going very briefly, but this is the whole process, though, because the full detail of this will take a full hour. But I'm giving you the overview, and if you get the overview of the different steps, like this is how you get the angles, this is how you get uh, the upper area, then you get the bottom area. Then all you have to do is subtract the bottom area from the full area. And that's how I got the 126 units. But I did a little rounding, so that's why the book got 126.03 or whatever. I did a little bit of rounding. What's the author's name of that book, by the way? The book, the Difficult Problems book. What's the author's name? Awesome. Let me check it out. But that's a step. What I described is the whole process. I understand it seems fast because there's a lot of steps. Actually going through it takes a few hours, at least because I have to remind myself how to do certain integrals and stuff like that. But that's the whole step how you do it. Uh, um, okay, what's the other way you had to get the answer? You think he's typing out the other way there, and I'll be closing up in a minute. While he's typing out that other way, thanks to all who showed. Thanks for dropping a line, the mathematician. I'll be back next week to do some more relativity. If you have a problem that you'd like me to do, let me know. If you'd like a full, thorough description of a problem or some tutoring, be sure to sign up on my Patreon. And instead of doing because right now I'm actually studying relativity. So a lot of the things that I'll do for a full class is because it's stuff I'm actually studying anyway in my classes. So it's actually helping me in the paper I'm going to be writing soon for my class to talk about relativity and Nicholas and Morley. I'll be writing about all of that stuff. If you want me to do something that is not part of my classes, I'm happy to devote a whole you know, uh, show to go into detail to that. Show me some love on Patreon or something like that, and I could do that for you. But otherwise, even if you have a problem that you'd like me to just review during part of the show, let me know. And I can do like I did here and go through an overview of a problem, or like I did last time, if it's a brief problem, I can go through it quickly. What's the question you have before I close up there, the mathematician? Let me change my background while he's working on that. Spacey. I'll pick another Earth one. Now, mathematician is typing a question. I'll let the video go for a bit while the music plays. Oh, check my Gmail. Okay. Let's see here. And by the way, the links to my email, if you want to email me something, that's you could get it on my website there. That's linked at the top. Links to my Patreon, links to my Discord. If you want to join the Discord, all of that is linked there. Uh, uh, well, he said, "Can you get?" Well, I'll respond to the email there. Awesome. So thanks for that email. Thanks for everybody who showed up. Hopefully you enjoyed the relativity. We'll keep up with that. Let me know if you have any general questions you want me to go over. If it's brief, I can go through it here. If it's long, I can give an overview. If you want an in-depth one, check out my Patreon. I can go through a full one. I also do tutoring. And I think after relativity, y'all can let me know what subject y'all want me to do. I'm going to go back to cosmology. I had a quantum exam yesterday, and it actually went all right. So our professor was really good. He wasn't trying to kill us. He gave us an exam on, it was different, but it was stuff that we were going on. It wasn't like a graduate level exam. So that was pretty cool. Maybe I'll go to cosmology uh, or quantum after we finish those few sections of relativity, and we'll keep it rocking. So thanks everybody for showing. Thanks everybody for joining. I'll see y'all next time.